There's a short video of here's a short video demonstrating about PRVs and how it cannot backflow through them.
Have a company already flowing water, it would be highly unlikely. Already flowing water. Crack this all the way open and you still their pressure. Additionally, once you make the connection, if you charge, if you open this valve before we even charge the lines, the water feeds back to you, help drop the pressure. As I said, it is absolutely critical that we ensure that this is not a pressure-reducing valve. How do we recognize it? There's various ways. You can talk about the big rim, but then I can tell you the Wilkins valves don't have a big rim. It says pressure-reducing valve on it. Yeah, they have a sign in the city of Miami that has a sign. The surefire way, after you look in there and you make sure there's nothing nasty in there, you feel threads. If you feel threads, that is a conventional outlet. If you don't feel threads, more than likely that is a PRV and you cannot use it as an inlet because basically it acts as a check valve when you increase the pressure on the downstream side of that valve. So that's the idea with improvising a first floor outlet. I've got a building in our territory that has that explains what a manual wet standby is. The fire department connection is way over on the opposite side of the parking lot entrance. There's no freaking way I'm going to use it. I'm going to stop right there where the gate is. We're going to hand stretch a line to the hydrant and put a line into the first floor in the outlet. I'm not going to use it at this. Okay, come on over here.
Did he just say that?
Repeat what he just said.
He was talking about a specific building that they have where the FTC is not convenient.
Okay.
And their primary plan is going to be the pump that are rising.
Right? Smooth. Smooth, right? This is a pressure reducing valve. If we were to put a line here and try to pump in, the force of the water coming in would slam this down. Say it's open. It's open. The force of the water coming in here would shove this down like a check valve. Go ahead, Mike. All the way. It's going nowhere. It's going nowhere. It's not pumped into the ground floor PRV. Okay, we're hooking up a conventional one right now. I'm just going to crack a little bit. The valve's open. Okay, this is a conventional valve. It has threaded valve stem. Crack it just a little bit, right? Crack it just a little bit, and quite predictably, water's going to flow out. Come in the inlet, go to the outlet.
Can't see it very well, but the water starts to come out. Oh, the other side.
Yeah, we got the other one.
There you go. Water coming out.
Okay, water's coming out, okay? If you pump into a conventional
They do is they come out, they want it to shoot all over the place. That's Bill Gustin, who the retired guy from Miami-Dade. He's got a lot of really good trainings and education and free webcasts for fire engineering. 4 or 5 of them on standpipe operations that are really good. So I recommend those if you're interested.
Something so simple. In 30 years, I've never heard to stick your fingers in there, feel for threads or not. I mean, it makes sense as soon as I said it, but we are always told learn your buildings, learn where they're at, look at the housing, all that kind of stuff. But that's simple. Just, yeah, as common sense as it gets, but I've never heard that until this video.
You know, they're complicated, devices. So.
Good info.
All right. Yeah, so kind of got a little ahead. Those videos and what we talked about was the plan B of pumping the riser won't work if it's a true PRV. And here, you know, in this building, you know, it's a PRV on top. It's probably a first floor outlet PRV on top and a regular valve on the bottom, so that they can pump this in a safe manner. So what they have here, supply comes in right here. This is the normal operating valve PRV. This is the regular valve, but there's a check valve. So the system goes to the check valve, and if you want to go in, you go in the standard valve. It goes through the check valve. So
theoretically, you can pump into that bottom outlet and discharge at the top of it.
And even if you open it, nothing will come out because of the check valve right here. So that was a little unique. They must have had a special building again where they didn't like where the FTC ended up or whatever. But they put this. So that just talks about what this is, and then if you're gonna pump a riser, you know, that's the next step that you can be thinking ahead. How much hose am I gonna need to get to that riser, and what adapters, you know, like double female pumped into it. So what are the implications of these? So pre and post 93, talked about that with Chris at break, is that, you know, if we do our elevation loss, 5 per floor, around 15 floors, that's going to equate to 75 psi elevation loss. So on modern buildings, that's our residual pressure. That'll be 175. So as we climb above 15 floors, rule of thumb, you know, we're going to start adding PRVs on the bottom. So in older buildings, you know, they're different design. They may operate on lower pressure. They may have to be even taller before we get true pressure reducing valves. Talked about PRV design plenty, I think, already. Yeah, most of these building capacities are either 500 or 750 psi, or 750 gallons per minute. Sorry. We know we need 90 to 100 psi at the gauge to operate our hoses. Standpipe bag tools. You know, we talked about the nozzle size that we use and the implications of pre-93 and post-93. We may have to take that building over a little earlier if the fire is advanced and we're going to open up 2 hose lines. So fire floor, floor above, like that. So we may want to take the building over by the FTC a little sooner than older buildings, since we're asking more water from that system. Talked about how to identify PRVs, and just to recap that, they're larger in nature, there's a bonnet, they say PRVs on them, and they have a smooth thread, a smooth stem. And then, not in our standpipe bag necessarily, but in the command room or on the truck, we have, you know, the right tools to defeat those if we need to. I talked to one of the manufacturers of these Zurn Wilkins PRVs, and they're not designed to throttle, like we said. So if you just have to crack that, the pressure in that stem can go up and down. So that's why we've added the gate valve to our standpipe bag, so we can use that to control the pressure more effectively and by design. And we've talked about a few things already that justify us pumping the roof all the time, regardless of the age of the building or PRVs. So if there's PRVs in the standpipe, PRVs in the sprinkler system, we need to pump the roof all the time. If we don't, you know, fire can travel, fire can spread, you know, upwards, obviously. So we may not be supplying the correct pressure to those PRVs, or supplying enough pressure for the sprinklers above the fire. So we need to know the location of these valves, how to identify them, and NFPA also says we need to be able to deploy 3 hand lines in a building if needed. So that kind of goes along with how the buildings are built, it said 750 GPM capacity for the buildings, right? With 2 risers, 500 from the first, 250 from the second. So that's assuming each line puts out 250 gallons a minute. That's 3 lines. So I've never done that. It's a training that we could at least put 2 lines in, and how would we do that? So not getting into tactics real quick, but once we start attacking fire from a stairwell, that's opened up, right? That smoke's gonna go up, it's a chimney, it's gonna go up and it's gonna go down a little bit. We wanna keep the other stairwell as preserved as possible. So the second line can come off from 2 floors below. And we know how residual pressure works. Once we open up another line and we're flowing, whether that line's going on the fire floor or back up the main line or above the fire floor, pressures are going to drop. They can go up and down. So your control man, you know, if this is the primary line, it's going up to the fire floor. This is the secondary line. If we have an additional gate valve, or we get our mutual aid companies to have a gate valve, that's where that can come into key. One guy can make sure one hose is not stealing from the other line. So he's got the 2 gauges here and the gate valve. You can control both valves from 2 hoses. And then the third one, that would be pretty advanced fire. Hopefully everybody's out or sheltered in place. You'd have to come off another riser or somewhere. Is there questions about that? It's not something we've done, but it's something that we should be able to do or be familiar with that setup.
Tommy, in the event that you would have to have that one for above the, like that third hand line, would that be a situation where to preserve the egress stairwell? Would that be one where we would come in with the line off of the ladder?
So you could. A lot of people think you don't want to tie up. I don't know. Ladders have been used for high-rise water access, and it's going to be a better option than having to lay another plan B, like an exterior standpipe or laying down a stairwell, I think, at that point. But it's been done before. That's another reasonable, method to get water if the ladder can reach, for sure. That's tactics. But I would think that the first 2 lines should come off the same riser in the fire tech stairwell, and if you needed a third line, it would come off the other riser, because you want to preserve that emergency exit stairwell for victims and stuff. With these being high risk, low frequency, read about high-rise fires. They happen all over, and FDNY has a good track record of wind-driven high-rise fires. The wind is different when you're 100 feet in the air. It's a high probability you could have heavy fire conditions that aren't touched by 2 hand lines that are flowing 325 gallons a minute. And Dave McGrail talks about that. It's amazing. They're putting 3 hand lines with 1.25 tips into one hallway, and they're not having the effect because it's a wind-driven fire. So then tactics change. But I guess the potential's there. And fire extension on the floor above, that's a command decision. If you're just looking, preventing, searching, investigating for that, maybe you don't need a 2.5, or you use that hose that's in the hose cabinet, for just spot fires or fire extension, but be able to deploy that 2.5-inch hand line. There's other things that have been recorded. Any questions? We're going to move on to the fire pump room in the FDC. So I've passed out a supplement. Like I said, the whole goal of this class is just to help us have a good understanding of some critical factors. And now we're going to get into there you go. The pump room and its components. So as we go through, you can make whatever notes you want possible. As you fill this out, we're going to have a breakout session later where we go to 212 South Merrimack and look at their pump room, and we'll be able to pick out these components. It won't be the same as our diagram, but once you understand the critical components in that pump room and how they're laid out, you should be able to work your way through a good pump room and find those components. So we've talked about why we need to know these so we can problem solve, overcome the problems that happen, such as failures. We verify pressures. We can do this at the fire pump or the riser. Identify and assess open or closed valves. And that information can be on the alarm panel or visually with closed butterfly or OSMY valves. Yeah, NFPA says we should. And diagnose problems and know the appropriate intervention. Yeah, fire pump room. It can be confusing. I really like this picture because there's colors and but it can be confusing. So using this picture, we're going to go along and label each component. We're going to go a little out of order because we're going to go from supply through the system. So knowing what to look for, where and why can help us sort through the mess and know what interventions we need to make if we're down there. Labels are nice, so some are labeled more clearly than others, but through good pre-planning you can ask for labels and help take some of the guesswork out of it. Alright, J. So if you look at the picture, J, this is the supply system backflow check valve. So here's a picture of one real life. They can have this configuration where it's angled up. They can look a little bit different, but in general, they'll tell you what it is. They don't have some type of valve like this. And I believe these, sometimes they're painted blue or they say don't paint them. But they should be labeled pretty well. And it just prevents the water from the building going back into the supply if there was a pressure drop. Or a water main break. We have plenty of water main breaks, right? It would be a terrible time to have a fire. I is the main control valve, so it just controls the water coming into the building, the fire suppression system, the main control valve. H is the jockey pump, the actual pump itself. So you don't have to be too concerned with all the little valves on it, but it's the jockey pump. It maintains the pressure on the system side at or near the system demand pressure. So if a system required to get us 100 to the roof, 100 psi to the roof is 250, it'll maintain it somewhere around 200 or close, so that you don't have to build all that pressure the moment a sprinkler opens. That pressure will already be there. We'll talk about that some more. System demand pressure. So it's important to know what this is. It's the PSI needed for fire streams and sprinklers throughout the system. And this is pretty accurately estimated by 5 or 6 PSI per floor. Elevation loss or head loss, right? Or head pressure. Per floor plus 100 PSI. So that's how we would estimate it. There's more accurate information on the acceptance test of the pump or the sprinkler test information, and it will be listed as churn pressure. So all these systems are hydraulically designed so that when the fire pump turns on and no water is flowing, that's the system demand pressure. So it's all based off that pressure. That, or once we start a fire, if there hasn't been a lot of sprinklers popping off, we can note the gauges in the fire pump room. And that will give us a good idea as well. When a sprinkler head is activated or standpipe valve is open, the pressure drops in the system below the level maintained by this jockey pump. and then the fire pump kicks on. We'll get more into that. The fire pump, it's a centrifugal fire pump just like on our apparatus. Is needed when the supply alone will not meet the system demand pressure of a system. So earlier we talked about automatic systems, which means the water supply provides the pressure in the water and nothing needs to be done. So semi-automatic is where a fire pump is needed. So the water is supplied, but what's needed is a fire pump to overcome that. That's actually semi-automatic. Common capacities for these pumps are 500, 750, and 1,000 gallons per minute. Sometimes more than that, but you know, in Clayton, the jail is 1,000 gallons per minute, and we have the parking garage. The new Centene parking garage is 1,000 gallons a minute, or has that capacity. So here's a picture of the fire pump next door. One thing I learned through this class was, here's a fire pump. You gauge on each side, right? So this is the suction side, and this is the discharge side. And sometimes it can be confusing on which, I mean, there's pipes everywhere. It can be confusing, but this inlet is designed, it's asymmetrical, right? It's got this bubble up top, and that's meant to catch small bubbles of air, keep them from going into the pump, I guess. But if you see this asymmetrical inlet, that's the supply side. And then this is the discharge side. I zoomed in on these gauges. It's not running. But the gauges are different, you know? Why can't they make them the same? I don't get it. But this is the suction side.
It looks like they're reading the same pressure.
Yeah, they are though. And that's a discharge side. So what we would be concerned with is this one. If we go in, fire pump's running, we just have, a small amount of water or sprinkler flowing, that might be close to what the system demand pressure is. Maybe it's, but that might be, well, we know we need to meet or exceed that pressure outside to overcome it with the current water flow. Or you just do your estimation. So the asymmetrical side is the inlet side. Note the gauges. These can be driven by electric motors with diesel motors and generators as backup. And they should have a constant slow dripping from the packing glands. Somewhere along here, it should go through a tube and just kind of have a small drip. And when it's running, it may be a steady stream. But if it's spilling out a lot of water, then something's wrong. Letter E is a test header. So this is what the technicians use to test the pump. They don't flow the roof every time they test the pump. They'll make it easy on themselves and use a test header to make sure that the pump is able to pump how it's supposed to. It's on the discharge side of the pump and has an internal valve that's protected from freezing inside the building. So the test headers have the valves on the outside that they can open and close, right? The technician will use. But if you follow the pump, or our discharge side of the pump, here's the valve for it, and then they have valves outside. So this, I'm getting ahead of myself, but D is a drain. It's just a drip drain because it needs to drain somehow. And this valve is the only valve in the system that should be closed normally. So it can be OSMY or butterfly, but if you see a closed valve, it might be labeled a test header, but it should be the only one that's closed in a normal operating system. And it's monitored closed. So if it's open, at the fire alarm panel, it may say, well, you have an open test header valve.
So if everything shoots craps and you need to pump into the test header, can you?
Yeah. And that's, that might be a pretty good option, especially on our older buildings. The test headers are sometimes on the outside, right by the FDC. So you need the same amount of hose. You might need some adapters, like a female to female. But it's right there.
But that's
So
why it's important to have somebody in that fire pump room.
that's why it's important to have someone down there and to pre-plan how to identify it and where it might be. Because it could be, this could be in the pump room, but where this valve is could be down the hall in another room. But, you know, those are labeled, and through pre-planning on some of our buildings, it might be something good to know, or something for us to practice identifying on our inspections, just in case. Like I said, if there's a PRV on that first floor, it's not gonna be an option to pump that riser. Test header control valve, this is letter C, we already kind of talked about that. So one of the important things is that it's normally closed and it's monitored to be closed. So once it's open, you know, it should have a signal saying that it's open.
Will that be a fire alarm or will that be a trouble or supervisory?
It would be a trouble alarm. So I believe a trouble alarms on alarm panels is usually an electrical problem or some type of electronic issue. Supervisory alarm would be valve control, I believe. So it would be a supervisory alarm on a test header valve. So, and those can be OS&Y or butterfly. Test header supply pipe is a B. It's labeled, so I put that in. And then the test header manifold is letter A. So there's a lot of valves on the picture and on the diagram. These are male threaded and have valves on the outside as well. And what's important to know is from the outside, the number of test headers will let you know the capacity of the pump. So you have to have an outlet for each 250 gallon sprint of the pump. So this one is 500,000, 1,500 gallons a minute. You know, it's probably something like a Menards or something. Needs to be able to flow a lot of water. But you see a test header has 2, that's 500, 3 is 750, right? Those are the most common ones. JLS 4, that's 1,000. That's how you can tell right off the bat. Any questions about that? And the fire department connection is letter F there. So the things about the design of the FDC is it's always on the discharge. It's always on the discharge side of the system, and there is only a check valve and never a control valve from its line into the pump. So that's this piping here. There's your FDC. This light blue area is a check valve. So whenever this system is charged, it's charged all the time. It's always pumping against that check valve. So if we supply a little pressure, we're pumping in that check valve and not in the building. Once we overcome the system demand pressure, then we're providing all the water, and you know it backs up against the fire pump and the other system. And at that time, once we take control of the building, maybe we want to shut that building pump down to keep it cool when it's just churning, because they're very expensive.
I was just gonna ask,
Or they're broken. You know, if they're broken.
long-term operations could damage the pump.
Right, right.
If you're not-
They're gonna heat up. So, just like our pumps, if it's not moving a lot of water, it's gonna heat up. That or if something goes wrong with it, you shut it down if it's leaking somewhere. So some weird things about the code is that NFPA 14 says a sign shall indicate the pressure required at the FDC to deliver the system demand pressure, but it is never listed. They've been stamped on the old buildings, Clayton stamped on there. And if you do your estimation based on that, it may let you know like, oh, this is an older building. So 65 plus our elevation loss is 180, the older building. Once we get 2 lines flowing, we may want to take that system over. But yeah, it's in there, it's in the code, but we haven't adopted where we make them put it on there. Also required an inlet at the FDC. Okay, so yeah, FDC is also in the code that each 250 gallons per minute capacity of the pump, you should have that many inlets. Not just on the test header, but the FDC. So if it's 750, you should have 3 inlets. And that doesn't happen either. And that doesn't happen, you know, kind of all over the country, but just kind of weird things. And usually there's only 2. Our modern buildings, we have more than 1 FDC though. So. And then letter L is the fire pump controller. This turns the pump on and off, automatic and manually. So it turns it on and off when the system pressure falls below a set range, indicating demand from the system, such as an activated sprinkler head or an open standpipe valve. We're going to talk. I've got some pictures explaining that too. K is a jockey pump controller. This monitors the system pressure within a designated range also, and turns the jockey pump on and off to maintain the pressure in the system when the pump is not flowing. So this maintains the pressure in the system near its required demand pressure. So that way it doesn't have to make up all that pressure when something starts flowing. We already talked about that. So here's a picture of the jockey pump controller. A lot of times, you know, the inspector will make it real easy and they'll put, you know, magic marker marks on here. So, yeah, you can tell right here. This system is sitting at, you know, 230 PSI. That's next door. And so this is the jockey pump controller. So once it reaches 210, the jockey pump kicks on and kicks it up to a certain level where it's happy, and just naturally that pressure drops. The jockey pump kicks on. You know, if the jockey pump goes bad or whatever is causing that system to leak, and it leaks below 210, that's the pressure set for the fire pump, and then it kicks on. So sometimes we get activated and the fire pump came on. It may just be because the jockey pump went bad, or there's a small leak somewhere. It's not able to boost that pressure. Does that make sense? All right. So with that, we can take a break and then eat lunch, and we'll reconvene for going over this.